Sir is an assistant professor at Department of Physics, MES College in Kerala. Dr. Nishad has joined this prestigious college in 2017 after serving as an assistant professor at Department of Nanoscience and Technology, Calicut University for 2 years. In 2015, he received his PhD in deposition of and characterization of semiconductor quantum dot and thin film structures. He received his master degree in physics in 2007 and also had MPhil degree in 2008 from Barkatullah University, Bhopal, India. Sir has completed and worked in various research projects, and as of now, sir has a total of 7 publications in hand. Some of his work includes research on nanomaterials and multi-layer devices. So I'll be handing over to the Mr. Nishad, Dr. Nishad for today's session. And sir, over to you, sir Nishad, sir.
Thank you, Pushpendra. Actually, we have 5 presentations here right now. I hope all are present here. Hello, am I audible?
Yes, sir. Yes, sir.
Okay, okay. Shall we start the presentation?
Yes, sir. We can start now.
Yeah. Okay, who is first right now? Who is first to present? Pushpendra?
Sir, you have today's schedule. You can announce their names according to their schedule.
Very good, very good. Then that's better.
Yes.
So I think we have Vikesh Chaudhary. Am I right? Vikesh. I mean, I'll just tell the name of the title P34. That is 220 keV nitrogen ion beam induced modification of zinc oxide nanoparticle, zinc oxide thin films. So is the candidate here?
Yes, sir.
Okay, okay, right. Who is presenting it?
Sir, myself, Vikesh Chaudhary.
Okay, okay, okay. Vikesh Chaudhary. Okay, right. Okay, please.
Can I start, sir?
Yes, yes, yes. You can start now.
Okay, sir. Thank you. So my slides are visible?
Yeah, your slides are visible.
Okay, thank you, sir. Good morning, everyone. The topic of my presentation is 220 kilo electron volt nitrogen ion beam induced modifications of zinc oxide thin films. The outline of my presentation, first I will briefly go through the introduction, which is followed by the experimental plan, results and discussions. Finally, I will conclude with the acknowledgements. The introduction, metal oxide thin film and nanostructures have attracted a lots of attention in the past few decades due to their unique physical and chemical properties and a vast range of applications in various fields of technology. Giordano has emerged as a promising material for range of applications in recent years. The application of Giordano is in electronic industries like UV lasers in solar cells and field emission display equipments, and biomedical applications like component of greens, component of nutrition products, and components of dental paste, and applications in photocatalytic application like water purification, deodorizing and air purifications, hydrogen generation, and other applications like textile industry, paint and coatings, rubber industry. In the past, spray pyrolysis, electron beam deposition, hydrothermal thermal evaporation, and RF sputtering technologies have all been established for the fabrication of high quality Giordano thin films. RF sputtering is a good choice for growing ZNO thin films because it provides convenient control of crystallographic orientation, good interfacial adhesion with the substrate, epitaxial growth of low temperature, growth at a low temperature, and high packing density of thin film grown. Different parameters such as pressure, temperature, deposition time, gas flow rate, and RF power can be used to improve the properties of thin films. Here is the experimental plans like ZNO thin film preparation. Firstly, ZNO thin film preparation. RF magnetron sputtering was used to ZNO thin film was deposited over quartz and silicon substrate using a ZNO target about 2-inch dia. Using an RF and DC magnetron sputtering machine at Material Research Center in MNIT. The thickness of the film was about 200 nanometers and 8.32 into 10 to power minus 5 millibar and 9.73 into 10 to power minus 3 millibar, and 30 minutes were chosen as the base pressure, deposition pressure, and deposition time respectively. And now after deposition, the irradiation of ZNO thin films. Following deposition, these thin film were irradiated with 220 kilo electron volt ion beam at various fluents like 1E13, 1E14, and 1E16 ions per centimeter square using a low energy ion beam accelerator at Inter-University Accelerator Center in New Delhi, India. And this is the setup for ion irradiation in IUC New Delhi. And now result and discussions. Firstly, Rutherford backscattering spectroscopy. RBS is effective technique for estimating material thickness and compositional parameters. This was accomplished using 3 MeV helium plus 2 beam. The spectrum was simulating using the Rutherford universal manipulations program to determine the thin film thickness. The film thickness was calculated to be around 200 nanometer with the RUMP software. Now, UV visible spectroscopy. The optical properties of ZNO are studied by UV visible absorption spectroscopy. The ZNO thin film was deposited on quartz and irradiated with nitrogen ion beam at different fluence doses for absorption spectroscopy measurement. The optical absorption of spectrum of irradiated and pristine thin film was investigated in the region 400 nanometer to 1000 nanometer. The graph shows that there is no substantial change in the band edge after irradiation, while absorption in the visible area increases. This means that the fundamental crystal structure remains unchanged. The lack of irradiation effect on the vibrational mode indicated the atomic order at the long distance is not affected significantly, as there is no shift in peaks position. This is the good agreement with the XRD data. The surface morphology. The surface topography and morphology of ZNO thin film was studied using FESM images of pristine and irradiated thin films. The pure ZNO thin film has a smooth and uniform surface with small ZNO grains, as shown in FESM micrographs of the thin films. When 220 kilo electron volt nitrogen ion passes through a thin layer, it loses most of its energy due to nuclear collision. The arriving ion transfer its energy to target material and produce surface as well as volume changes in the thin film. In this way, irradiation with 220 kilo electron volt nitrogen beam produce a uneven wrinkled network structure. Now, Raman spectroscopy. For pure and 220 kilo electron volt ion beam irradiated thin film, a typical spectra exhibited two bands at 580 centimeter inverse and 438 centimeter inverse. The characteristics mode of ZNO vortice phase is observed at roughly 438 centimeter inverse, which is related to E2 high mode, which is also exhibited and significant peak at 33.92 degree in XRD spectrum. With 220 kilo electron volt nitrogen ion beam irradiation increase the intensity of A1 low mode, while the E2 high mode decrease in intensity, which is responsible for reduced uh, crystallinity and defect formation of ZNO matrix. And now XRD diffraction analysis. The XRD diffraction analysis technique was used to analyze the structural properties of as deposited and 220 kilo electron volt ion beam irradiated thin films. XRD, the XRD pattern for pure ZNO and 220 kilo electron volt ion beam irradiated thin film at different doses like 1E13, 1E14, 1E16 ions per centimeter square with different reflection planes. Pure ZNO thin film revealed the crystalline nature and demonstrated the hexagonal vortice structure. Irradiation does not affect the peak position or intensity. This demonstrated that irradiation has no impact on ZNO bonding. Now the conclusion. In the present study with 220 kilo electron volt ion beam irradiation at varying dosage, structural and optical alternation in ZNO thin film were studied. We used RF magnetron sputtering at room temperature to create pure ZNO thin film. RBS modeling revealed that the thickness of ZNO thin film is around 200 nanometer. The structural and optical quality of the 220 kilo electron volt nitrogen ion beam irradiation in ZNO thin film was improved when as compared to the as grown ZNO thin film. The formation of hexagonal vortice structure with good crystalline character is revealed by the XRD spectrum and Raman spectrum. FESM was used to examine the surface features of film, which reveal considerable changes in the thin film. At the end, I would like to acknowledge it to MIT School of Applied Sciences, MIT University Jaipur, Optical Material Lab, MNIT Jaipur, IUC New Delhi, MRC, MNIT Jaipur, and the financial support by DST New Delhi and UGC DI CSIR. And these are references, and thank you. Hello, sir.
Yeah, I guess nice presentation it was.
Thank you, sir.
And I have a couple of questions. I have some doubts.
Yes,
and yeah, initially I have a doubt on the UV visible absorption spectra where there are multiple peaks observed in the range of 600 to 400, I think.
Yes, sir.
So why these multiple peak? I mean,
Sir, UV
is it any interference pattern or an absorption behavior?
Sir, this is absorption behavior.
Okay. Can you show that one?
Yes.
Yes.
Yes, sir.
So it is observed there are a multiple absorption peak behavior. So one
Yes,
is
sir.
around somewhere 450 and another one at 540 somewhere. Is it a UV visible absorption?
Yes, sir.
Okay. And one is around 800, right?
Yes, sir. Sir, mainly we can consider there is no peak shift with irradiation.
Yeah, that's fine.
Yes.
There is no peak shift means there is no any change in the
change in like red shift, blue shift in SPR.
Okay, fine. That's fine.
Yes.
Again, is there any presence of nitrogen in the crystal? I mean, have you studied about like that? Any nitrogen effect?
It's a nitrogen irradiation method, not implantation of nitrogen ions in thin film.
You are doing the irradiation of nitrogen ion, no?
Yes, sir. Irradiation, not implantation.
No, I understood it. But is there any surface attachment of this nitrogen during this irradiation process? Did
No,
you
sir.
observe any presence of nitrogen?
No, sir.
Okay. That's fine.
Yes.
Yeah, that's fine. It's good.
Thank you, sir.
Good presentation it was.
Thank you, sir.
Thank you.
Can I stop, sir?
Yeah, you can stop now.
Okay,
So the next next presenter have on the list Amena Selling. Amena, what I don't know how to pronounce it. 120 keV AR ion.
Yes, sir.
Radiation of yeah. Amena, you can get
Just
ready
a minute.
for your presentation.
I'm sharing my. Sir, my slides are visible?
Yeah, you are visible, Amena.
The topic of my presentation is 120 keV argon beam irradiation of magnetode sputtered ZNO thin films. Basically, in this we have prepared the ZNO thin films and using 120 keV argon irradiation. These are the contents of my presentation: introduction, experimental work, results and discussion, conclusion, and references. Basically, these are the basic properties of ZNO material which we use. It is basically a semiconductor material. It has a wide band gap of about 3.37 electron volt. It has a refractive index of 2.30. It has resistivity in the range of 10 raised to power minus 4 to 10 raised to power 13 ohm centimeter, high transparency, and it has found in the 3 crystallite phases: hexagonal wurtzite, zinc blende, and rock salt. Why ZNO is interesting? It is basically used in the medicinal purposes, or basically in the laser diode devices, LEDs, transparent coatings, and basically in future it is used in the field of nanotechnology, in UV detectors, nanoscale detectors, and other. Due to its higher band gap, we use ZNO thin films. The basic properties of ZNO thin films: it has wide band gap, as I told earlier. It needs development and research. It is very low cost material. It is fabricated at low temperature, room temperature. It has flexibility and large area. These are the application of zinc oxide. It is basically used in transparent electrodes, LEDs, OLEDs, solar cells, flexible electronics, etc. These are the different methods of film deposition in which we used chemical vapor deposition and physical vapor deposition. In our work, we use basically physical vapor deposition as RF sputtering. Sputtering is basically the ejection of atoms from the target surface from targets on the bombardment of ions. We basically use RF sputtering, radio frequency sputtering. The basic structure: the necessary high frequency voltage source is connected in the series with capacitor and the plasma. The capacitor serves to the separate DC component and keeps to the plasma electrically neutral. Why we use RF sputtering for our thin film deposition? These basically advantage of these are: it is basically sputtered, insulated, semiconductor, etc. It's the substrate heat up very less. Due to the low oscillating electrons, the sputtering rate is very high in compared to the DC sputtering. Give better film quality, able to deposit wide variety of metals, insulators, alloys, and composite, and can give large area target for the uniform thickness over the substrate. These are the experimental details of my work. We have deposited the thin films of ZNO by RF sputtering techniques using a rate of 5.0 SSCM flow of argon gas is maintained in the chamber to create the plasma. Basically, the pressure before and after deposition is 8.32 into 10 to the power minus 5 and 9.73 into 10 to the power minus 3 respectively. RF power is used as about 100 watt when deposition is performed. Then we irradiate with the thin films of ZNO with 120 keV argon beam at different doses ranging from 1 into 10 to the power 14 ions per centimeters to 1 into 10 to the power 16 ions per centimeter at IUSC New Delhi. Then we study the modification in the ion beam samples by using characterization techniques like RF sputtering, Rutherford backscattering, UV visible scanning, electron microscopy, atomic force microscopy, Raman, and XRD. These are the results and discussion. First, we have characterized with RBS. This is the simulated RBS spectra for pure ZNO, in which we have simulated the spectra, and the thickness, estimated thickness, is found to be about 200 nanometer. This is my XRD pattern of pure ZNO as well as irradiated thin films, in which these planes, for structural analysis, we have done this characterization. Two major planes 002 and 102 are found, and we can see that after irradiation the planes are remain stable. This gives the stability in the structure, and it is the plane 002 gives the hexagonal Wurtzite structure of ZNO and having crystallinity. From this we can see that there is an improvement of crystallinity and quality of film, because there is no shifting in the peaks, XRD peaks. We have calculated the crystallite size from the Scherer formula given in the presentation, in which we get the crystallite size which variation from 5.7 nanometer to 9.9 with increasing the doses. This is the UV visible spectra, in which we can see that in pristine we have observed the absorption band, but after irradiation the peaks, the absorption bands get sharp. It reveals that the absorption increases. There is no significant change in the band edges. There is a very small shift which gives the good agreement of XRD structure, XRD results. The ion irradiation induced defects creation. This increase in the absorption reveals the irradiation induced defects creation, like anti-site oxygen and oxygen vacancies in the film. These are the surface morphological investigation, in which we can see that after irradiation, there is grain rises, very smaller grain rises in the images due to the Ostwald ripening of crystallites. This is the Raman spectra of, we can see that from the theory, we have ZNO having a hexagonal Wurtzite structure which is associated with the 6V4 symmetry. These are the modes. Raman modes for Wurtzite structure are 2A1 plus 2E1, in which optical modes and acoustic modes are included. We have seen from the figure two modes are observed at 437 centimeter inverse and 578.1 centimeter inverse. The 437 is due to the E2 high modes, which confirm the formation of the Wurtzite structure. With irradiation, all these modes are appear in all the images. This gives the stability in the structure of the ZNO. There is also an other peak of 578 centimeter inverse. This intense peak becomes sharp at with increasing in the irradiation. It is assigned due to the A1 allo mode. These are the conclusion of work. We have just synthesized the ZNO thin films by RF sputtering, then irradiated with 120 keV ion beams. Then we have from the XRD, we get the structure of pure ZNO, which is hexagonal wurtzite. After the irradiation, the estimated thickness of ZNO is approximately 200 nanometer. The smoothness and homogeneity is found after the irradiation due to the with the help of FESEM images. Improvement in the crystallinity of thin films with the ion irradiation is found with Raman spectra. Increase in the absorption gives the signature in improvement in optical properties with the ion doses. These are the references. Thank you.
Thank you, Amana. It was again a good presentation. I think you both are from the same group.
Yes, sir.
Okay. Are you research? You people are the research scholars, I think.
Yes, sir.
Okay, fine. So you work at Amity? Are you working? I'm
yes,
sorry. Are you working at Amity?
Sorry, sir.
Amity, are you working at Amity?
Amity, no, sir. No,
Amity,
sir.
no, not Amity.
I'm enrolled from MNIT.
Oh, I see. Okay, right, fine. That's good. Well, so the results seems couple. I mean, somewhat similar. So
Yes,
the
sir.
same thing I have the question there in the UV visible. I mean,
Yes,
mostly we. Here we find some multiple peaks in UV.
yes,
You
sir.
see, what is the method you have used to analyze this UV visible spectroscopy?
Sir,
Yeah.
these are the
You have the
modes for
pencil.
ZNO.
Yeah. Okay.
Yeah, these are the all pure mode or modes of pure ZNO.
Okay.
After irradiation, we just see the modification in the peaks, or we can we can doped with some metal or something. Then we can see the modification in the peaks. It gives SPR peaks or something like, so we can observe this.
Okay.
So these are the pure ZNO. So all modes are visible, and we can see that the optical absorption increases after irradiation.
Yeah, that's fine. So that may be due to the compactness, increasing the compactness of due to the irradiation process.
Sir, it creates defects or something. If we can vary the energy like 120 to another MeV, or it creates some other defects, or it's depend on mechanisms.
Okay. So my suggestion to both of you, that Vikesh also there. So
Yes,
there is a multiple peak observed within the range 400 to 800 somewhat.
200.
So please,
Right.
please check what is the reason behind this multiple peak.
Okay.
So there are two possibilities. One is the optical absorption behavior.
Yes, sir.
But usually the zinc oxide does not have the optical absorption behavior within this particular range. Okay. So this multiple peak may be due to interference behavior. This is what I was supposed to tell with the Vikesh as well.
Yes, sir.
So this may be due to, I don't know whether it is due to the interference effect. If it is due to the interference effect.
Yes, sir.
If it is due to interference effect, you can find
Yes,
the thickness of the film from that.
okay.
I don't know whether it is due to the interference behavior.
So, but from some literature they get deposit from some other techniques, but modes are in the region from 400 to 800, as many papers I have read.
Oh, I see.
But the techniques is different for deposition. Some there is thermal evaporation method, some E-beam evaporation method, or pulse laser or other.
Okay. So please go through that once.
Okay,
For
okay,
your
okay,
further
sir.
studies when you submit, when you do submission, your PhD and all.
Sure, sir. Yes, sir.
Another one that was about the Raman spectra.
Yes, sir.
So there is a slight shift we can observe in Raman peaks as well. Did you observe it?
Sir, which shift?
There is a slight peak shift, you can observe it
Sir, but just
with
from
the
the
radiation. With the radiation.
yes, sir. Yes, sir.
Do you find any shift?
No, sir. It's about in range of 578 to 580. But from literature, no,
The peak at 437.
this is so somewhat there is a noise in this we can found.
Yes.
But from the group theory or this, the optical modes are at particular range that like we have discussed at 437 and 578 something, which is due to the E2 high mode and these are observed in our sample.
I see. So I have one more suggestion in this particular.
Yes, sir.
You need to analyze why this shift is. See why I'm asking.
Yes, sir.
Why I'm telling you, there may be some possibility of defect induced.
Yes, sir.
See, the defect plays a crucial role in this peak. Basically, when I have seen the abstract from the Vikesh as well, they have
Yes, sir.
been shown it is XPS also.
Yes, sir.
I don't know whether you people are doing with working with XPS. I don't know, but from the Raman spectra and as well as XPS spectra, there may
Yes,
be
sir.
possibility of peak shift because of this defect concentration.
Yes,
So
sir.
if it is so, and I have seen in your sample, I have noticed in your sample there is a significant peak shift in this Raman spectra, and
Yes.
please check it whether it is because of defect concentration or not.
Okay. Okay, sir.
This is my suggestion. You may do it in your
Yes,
further.
yes, sir.
Okay. If it is so, it would be better.
Yes, sir.
Anyway, by the way, it was a nice presentation.
Thank you, sir.
Okay. Right. So I think we shall move to the next participant. I think it was Shadab Khan.
Yes, sir. Okay, sir. Thank you very much. So I'm going to present my screen.
Just wait,
please
Shadab. Just wait,
Okay.
Shadab. Shadab, will you just make your presentation visible?
Sir, is it visible, sir?
I think it is not visible, Shadab.
1 second. Is it visible now?
Yeah. You
Thank you
might
very
just
much, sir.
go to okay.
Thank you very much. So, good morning, dear sir and all dear participants. My name is Shadab Anwar Khan and I'm presenting on the topic of synthesis of silver nanoparticles by green method and their structural and optical properties. So nanoparticles are very important and very popular in technology nowadays. We are seeing everywhere there is some kind of introduction of nanoparticles in each and every technology because we want everything smaller and much more efficient than it is. Everything is getting smaller and getting faster, quicker, and nanoparticles have played a major role in that aspect. Now the metal nanoparticles are very much, I would say, popular in actually introducing the antimicrobial and antibacterial properties, especially in case of silver or gold nanoparticles. But one thing that that gets sometimes actually ignored or neglected, I'd say, is that they also have very good properties in terms of energy harvesting or optical or electrical properties. If we see that silver nanoparticles, silver is the best conductor that we have. It is the best electrical conductor or thermal conductor. So it already has those properties, and if we use those properties in terms of nanotechnology, we can really utilize that for different purposes in photovoltaic technology, for organic solar cells, for electron double layer capacitor, or these kind of spaces as well, along with their antimicrobial and antibacterial properties that are very much in use already. What are the objective of my study? So what I wanted to do is that I wanted to prepare silver nanoparticles by green synthesis, that is by using only green agents. What I did, I used Ligustrum sinensis extract, the leaf extract of Ligustrum sinensis, Chinese private, or it is also known as, it is a plant which is used for decoration, or it is very easily found. That's why I used it. And I did their structural property through XRD and UV visible spectroscopy, or SEM and TEM, and also did some study of their optical properties through UV visible spectroscopy. So the procedure of production of nanoparticles that I used was to prepare a silver nitrate solution, molar solution, whatever kind of molarity you want. If you want to prepare 1 millimolar solution or a 10 millimolar solution, you add this amount of silver nitrate in distilled water according to the measurement or the molarity of the solution. And in a separate beaker, you take the extract of the plant, the Ligustrum sinensis leaves extract. I took by beating the leaves, and after beating them, heating it for 10 to 15 minutes, and taking that extract, filtering it with Wattman filter with the filter paper, and then adding that extract to the silver nitrate solution. After adding those two separate solution into one beaker, we heat that solution for 20-25 minutes, probably 30 minutes, until the color of the solution turns reddish brown. Because when we are actually taking the extract out of green leaves, the solution is mostly of green color, because silver nitrate doesn't have any color. It is transparent, and the extract has green color. But when we actually add them, the silver ions turn to silver metal nanoparticles. They turn to reddish brown. The color turns to brown. And it signifies that there is the production of, or there is synthesis of silver nanoparticles. And after the synthesis of silver nanoparticles, as you can see in one beaker, there is that reddish brown solution. We can get the solid nanoparticles through centrifuging the solution, and then taking that residue and heating it afterwards. Why we chose the reducing agent and nanoparticles, or silver nanoparticles to be exact? The reducing agent, the Ligustrum sinensis that I chose, was because it has properties of that it is very much antibacterial. It is very toxic to those kind of agents, those viruses, or those bacteria, those microbes. It is very harmful to them. So it can be very much help the whatever purpose we are using it. This agent will help it to be free from any kind of reaction with those bacterium or virus. Why I chose silver nanoparticle is because, as I said, silver is the best conductor, thermal conductor, electric conductor out of all the metals, all the noble metals. The other options that we have is, of course, gold or copper. Copper is another very good conductor, not as much as silver, but it is also a very good conductor. But it is very reactive to the oxygen, and it makes oxide very readily. So it is very much vulnerable to the environment. Whereas silver is much more reticent. It is much more immune to getting that kind of reactions and getting spoiled quickly. It has a longer lifetime. So that's why I used silver, and it is also cheaper than gold. So that is another important thing. So the characterization that I did was this through UV visible spectroscopy, and you can see that there is a intense peak, single peak at around 305 nanometer for in the UV visible region, which signifies that there is an intense peak, that the nanoparticles that are actually made of uniform size. They are not varying too much in size, and we can see that their production is very much significant because we are getting a single peak, a very intense peak, and we can also calculate the band gap through the data that we received, and the band gap was calculated to be around 2.5 electron volt of the peptide nanoparticles. Then the XRD analysis was done, and we received the characteristic silver nanoparticle in peak at 38.5 degree angle to theta, and which signified the crystal structure of the silver nanoparticles that we made. And we also calculated their size through using that Schreier equation that is given in the PPT presentation, calculating the angle and calculating the full width at half maxima. The size of the particle was about 21.5 nanometer. That was the calculation through the data that we received from XRD. Then also the imaging, STEM and SEM imaging was done, and we can see that nanoparticles were well dispersed and very much spherical in shape. There is very few nanoparticles are of deformed shape. Most of them are very much homogeneous, and they are very much in spherical shape. Their size we can see as we compare it to the scale. We see that it is in the vicinity of 20-25 nanometers. Through the SEM data, we can actually confirm that as well. Moving on, summarizing my results. So we were very much successful in synthesizing nanoparticles through gene synthesis using Silica-Strum Sinens. Nanoparticle size was calculated to be about 21.5 nanometers, and through XRD data. And we also calculated the d-spacing, so using the Bragg equation, the d-spacing of the nanoparticle in the 111 structure, crystalline structure, was about 0.23 nanometer. So we hope that this kind of techniques of making readily nanoparticles can bring can be fruitful for harvesting renewable energy for the future. So those are the references of my studies. Thank you very much.
Shadab.
Yes, sir.
Okay, it was again a good presentation. So you from Department of Physics, Hari Singh Gaur University, Sagar,
Yes, sir.
right?
Yes.
So are you doing your PhD work?
Yes, sir. I am doing PhD under Dr. Sandhya Patel, ma'am.
Okay, Dr. Sandeep. Okay, right. Well, we have seen your results, and I mean, how long you have been doing your PhD work from?
So I was enrolled in November 2019.
Okay. So in between there was a lockdown as well.
Yeah, there was lockdown, so
Okay, you
yeah,
are in the beginning
so
stage.
almost 2 years of my
Fine,
research
fine.
here.
Yeah.
We were just sitting there. I was just.
Okay. Right. Fine. So you used ligastrum sinens.
Yes, sir. Yes, sir.
So actually, what we locally called this. Do you know what we call it?
It is also known as a Chinese private, or it is a decorative plant. It is not a herb. It is actually a shrub. So we do
Okay.
not use it for any kind of medicinal purposes.
Okay. So you just took the extract,
Yes, sir.
right?
Yes.
Okay, then that extract you used as the
Reducing
reagent,
agent.
reducing
Yes,
agent.
Yes.
Okay, fine. So you mix with the silver nitrate, and it automatically got the silver nanoparticles. And I have a bit doubt on your XRD. I mean, I don't know whether it is possible to estimate the crystallite size of with this particular broadening.
So
I mean to say, what
yeah.
I mean to say,
Yeah.
actually, the broadening we could observe here. It is approximately it is equal to the instrumental broadening itself.
Yes, sir.
Okay, please check it. I don't know whether
Okay.
it is whether it is. I mean,
Okay.
a particle with or a, and the one other thing you have mentioned that d is the size of the particle in the nanometer. Basically, by using the Schrodinger's method, you cannot estimate the size of the particle. You can estimate the size of crystallites only.
Okay. Okay, sir.
That's a suggestion I have.
Yes, sir. Okay,
Remaining
so I will revisit it.
Yeah, you please correct in when you do your further research.
Okay, sir. Thank
You
you.
can estimate only crystallite size. That's it from the
Okay,
broadening.
thank you.
Okay, fine. I hope that's fine.
Okay, thank you, sir.
Thank you. Shall we move to the next participant? Rishiraj Singh Rathore. Am I right? Rishiraj. The optical and dielectric studies on ternary hybrids of cobalt iron oxide, silicon carbide, and barium titanate nanocomposites. So I hope Rishiraj is there.
Sir, Mr. Risiraj is not present right now. We can skip his name and go to the next.
I see. Okay. I see. Okay. So we'll move to the next participant, that is Arunima Patel. Aruna Patel, I'm sorry. Aruna Patel.
Yes, sir, I'm here. Good afternoon, sir.
Good afternoon. Aruna, you just present your screen.
Yes, sir. It is visible, sir. Is it visible, sir?
No, actually, it is not visible right now. Please check.
Now, sir.
No, Aruna. Yes.
Okay, sir.
Yeah.
Yes, sir. I am presenting my talk on. Hello.
Is it on PDF mode? I think.
Yes, sir. Actually, here is no power, so I am presenting with mobile.
Okay,
that
fine.
is the issue, sir.
You carry on, please.
So I am presenting my talk on paper on hot deformation and processing map of AA7178 alloy and AA7178 10 weight percent SiC composite. Here I am clearing one thing, that AA stands for aluminium alloy. So this 7178, it is a 7000 series of aluminium, which has standard notification of 7XXX. Here 178 representing 1% of magnesium, 7% of zinc, and 8% of copper. So that's why it is called 7178 alloy. So this is the standard notation for this alloy 7000 series, and 7178 10 weight percent SiC composite. So here I am comparing the hot deformation and processing map of these materials. So what is the significance behind that and the importance of this material is it is used in engineering application. Before joining this institute, I am the part of CSIR Ampere Bhopal, and one of the engineering application project in 2007 to 2012, I was on that project. So this is that part of that laboratory, work of that laboratory, and it's a 11th 5 years project of that organization. So in this, we have done the effective material for engineering application, and the 7000 series is used there. So why this is for engineering application, lightweight engineering material for engineering application. So we are making the aluminum alloy applicable for engineering applications and introducing a 10% of SiC composite. So we have to find that where it is suitable for working the material. So we have to do the hot deformation of that. So for doing the experiment, we have done this by oil-fired furnace. We have to prepare this material and using the BIS 50 kN hydraulic machine for compression test of the material. So the experimental setup of this machine is a stair caster for making a composite. In this, the 7178 alloy we have prepared first, then remelt it and adding the 10% of SiC particles on that. The particle size is of 10 to 20 micron, and the universal testing machine of BIS make 50 kN is used for the compression test. So we have to make the samples of 10 mm diameter and 15 mm of length, and compressed at 200, 300, 400, and started from room temperature and different strain rate, that is of 0.01 per second to 10 per second. So using the 4 and 5 different strain rates and the temperatures, we have to do the plots for that. So we have to draw the flow curves for that. Here in the graph, I am presenting the 4 different flow curves for 7178 alloy at 100 degrees centigrade and 400 degrees centigrade. So we see that on increasing the strain rate, how the flow curves are presenting. Its order is of increasing, means on increasing strain rate, the flow curves has a compressive stress that is increasing. And on increasing temperature, it goes decreases because the material gets softens. So the stress curves are decreases. And in the second graph, third one, that is 7178 10% SiC composite at 100 degrees centigrade, similarly at 400 degrees centigrade. So these two curves representing for the below curves are for the composite and above for the alloy material. So the flow curves we can roughly says that on increasing temperature, the flow stresses decreases, and on increasing strain rate, the flow stress increases. So these are the two interpretations we get from these curves. And the processing map. So what are the processing map? The stress and the strain values we have obtained from the stress analysis are plotted in the form of graph, that is the RRL software, and thus from that software we have to draw the processing map. So here in the processing map, in the X direction, we have seen the strain rate, and in the Y direction, we have seen the stresses of the material. So the curves line concentric curves are representing the efficiency of the material, that we can easily draw or compress or the ductile the material in this range. So in the results, I have discussed that thing, that the efficiency is almost here 25 to 28% in different regions, but the temperature is of the higher region, means at above 250 to 400 degrees centigrade, we have got the efficiency range. And the microstructure in the 4 different regions. So these 2 microstructures are when these materials are not deformed, means in the initial stage. The first one showing the optical micrographs of 7178 alloy, aluminum alloy, and the second one, B, is representing the 7178 plus 10% SiC composite. And the lower one micrographs showing the DRX, means the grains are getting filtered, means reduces to smaller size. And at higher strain rate, the flow of the material shows the mechanism at 100 degrees centigrade and strain rate 10, the flow showing the dynamic recrystallization or recovery of the material. The higher micrograph SEM is showing the interface, that how the SiC particle and the matrix of the aluminum material has been goodly bounded. So the discussion part is that transfer of the load from ductile matrix to the hard particle, means when we have to deform the composite material, the SiC particle has easily transferred the load to the matrix at higher temperature and at different strain rates. So we get these type of phenomena. And microstructural transformations such as recrystallization or damage phenomena are seen, and the flow curves representing that the flow of the material are easily at higher range, means 350 to 400 degrees centigrade, and the dynamic recrystallization also seen there. And at lower temperature, there is dynamic recovery of the material, that is DRY, And at higher temperature, we have seen the DRX, that is dynamic recrystallization. And higher temperature, the grain are also refined to smaller size, and they preferentially arranged in a proper manner, or but in case of matrix, they are nucleated around the SiC particle. So this is the little part for the for cracking or deformation of the material. So here the sometimes SiC particles hindering the flow of the material, and sometimes it create a very good flow to the material. So these conclusions and the efficiency at around 350 to 400 degrees centigrade for the alloy material for the composite material is 22 to 24%. And in case of alloy, it is more than that. So these are the interpretations, and the conclusions is that the hot working characteristic of AA7178 alloy and 10-weight% SiC composite were identified by the processing map. So we can say that on adding the 10-weight% of the SiC composite, its strength, hardness, and the flow stability are better than the alloy. So this is the validation with the dynamic material model, or we can say processing map. And the dynamic recrystallizations occurred at moderate values of dissipation efficiency in processing map in case of composite, whereas in case of 10-weight% SiC due to abnormal grain coarsening. So this is one of the reasons. It may be noted that here the matrix material does not show a superplasticity domain, as it was represented in Y.R. Maharajan paper. So the reason for the appearance of the superplasticity domain in the extruded material is the fine grain size produced by the recrystallization after extrusion. So for secondary processing of the material, the 7178 composite and 7178 is alloy are better at 250 to 350 range and with good processing map efficiency. So this is the references I have used for this work, and this is all about my work. Thank you so much.
Thank you, Dr. Aruna.
Thank you, sir.
You have done a very good job. And I hope you have done this work at RRL, I mean, Ampri, Bhopal, right?
Yes, sir. During my
Okay.
thesis work, sir.
I see. Okay. So that's fine. So which, whom we are working with?
Sir, presently I am working with Government College, Purvai, that is
Yeah,
affiliated to
I have
Barkatullah
seen,
University.
I have seen it. Earlier you were working with which group in
Earlier,
Ampri?
I am with Dr. S. Das, sir. He is my guide. Dr.
Acha,
S.
that's
Das.
okay, right.
Mm.
Fine. That's fine now. And so basically you are doing this composite material, you are preparing for the softening the material. I mean, I have a bit doubt on that flow diagram of that at 100 degree.
Flow. This is a flow curves.
Yeah, flow curves, yeah.
Yes,
So
sir.
there the stress strain curve,
Hmm.
I have only doubt. I mean, what it does mean here? I mean, before that, when the stress goes
Sir, when
beyond
we do
the
the stress strain, sir, that is a 0.01 is valid zero strain, means it is a speed of deforming the material. So 0.01 representing very slow pressing of the material, and 100 per second representing the high, means speed is high. So that sky blue curve you are seeing in the diagram, that is a somewhat disorder, zigzag, because when high strain rate we are pressing the material, that sometimes it will tilt, sometimes it gets soft. The temperature is not very high, it's 100 degrees centigrade. So the deformation in this condition means the material may be break, but the temperature is 100, so it is little bit soft. When it is done in 400 degrees centigrade, you see this zigzag order of the material is getting somehow changed, and the strain up to here is 0.5, means आप इसको इतना ही खींच सकते थे, इसके बाद ये सॉफ्ट हो जाएगा. तो प्रेस करने पे एक कॉइन जैसे होता है 1 रुपीस का, इतना फ्लो करके मटेरियल जो है वो एक शीट के फॉर्म में बैंड हो जाता है. इनिशियली तो हार्ड रहता है, बाद में ये इतना सॉफ्ट हो जाता है कि ये कॉइन जैसे बन जाता है हाई टेम्परेचर.
Okay. So did you, I mean, is this work focused on particular applications?
Yes, sir. It is focused on lightweight materials for engineering application. You
Lightweight
see
materials.
the alloy wheels. Yes, sir. This work is of 10 years back, 2012.
Okay.
Right now, alloy wheels are coming in the automobile sectors.
Okay.
So this one is the best application of that. And ARAI, that is Automotive Research Association of India in Pune, it is also working in this thing, sir.
I see. Okay. Excellent work. I mean, actually, I know Aruna personally. I am also from Barkatla University. Okay, right.
Okay, sir.
By the way, nice to meet you.
Thank you, sir. Thank you so much.
Right. Thank you. And I think almost all the participants finished their presentation. Is Rishiraj participating now?
Yes, sir. He's joining. He said he'll be joining in 2 minutes. So we can wait for 2 minutes and then we'll start with his presentation.
Okay, fine. Right.
Hello, good afternoon, everyone. Am I audible?
Good afternoon.
Good afternoon, Nishad sir.
Yeah, good afternoon. Rishiraj.
Yes, sir. I'm Rishiraj sir.
Okay, fine. Okay,
So,
Rishiraj, start now.
Okay, I'll start with my presentation. I'm Rishiraj Singh Rathod from Amity University, Rajasthan. I'm doing my PhD under the supervision of Dr. Deepshika Rathod. And the topic of my presentation is optical and dielectric studies on ternary hybrids of cobalt ferrite, silicon carbide, and barium titanate nanocomposites. So this is the flow of my presentation. I'll be talking about the introduction, and then after that, I'll be going to the methodology part, then experimental techniques, results and discussion. Then I'll be concluding with references. So as we know that research in the field of composite materials has attracted a lot of attention from the researchers because of demand for efficient and cost-effective materials, which can meet the present and future needs of industry. In this research work, we were interested in making a composite of ferrites, titanates, and carbides in varying proportions and study their optical and dielectric properties. So we have targeted to synthesize cobalt ferrite, silicon carbide, and barium titanate nanocomposites at varying weight percentage of barium titanate using chemical coprecipitation and solid state method. To perform the synthesis, we have used industry-grade barium titanate and silicon carbide, while the cobalt ferrite was prepared in the laboratory. And for the characterization purpose, we have characterized our samples of nanocomposites for X-ray diffraction, UV visible spectra, and FTIR and dielectric studies were also performed. So for the synthesis of cobalt ferrite, we have adopted chemical coprecipitation technique. Now there are several other methods by which cobalt ferrite can be prepared, but due to several advantages like synthesis speed and control and quality of the product, we have adopted chemical coprecipitation technique. Now you can see at the bottom, the following chemical reaction was involved in the synthesis of cobalt ferrite. For the synthesis purpose, we have used anhydrous cobaltous chloride and ferric chloride. The aqueous solutions of the precursors were mixed together for 15 minutes, and the chloride precursors were then added to hydroxide precursor. And then again a stirring was performed for 15 minutes. The resultant compound was centrifuged in order to remove the NaCl part and H2O part from our product. The resultant was, after grinding, the resultant was cobalt ferrite nanoparticles. Now, the cobalt ferrite nanoparticles were used to synthesize a nanocomposite mixture with silicon carbide and barium titanate. Now, for that purpose, we have already mentioned that we have used commercial silicon carbide and commercial barium titanate. We have grinded the mixture with ethanol for 2 hours, and what we achieved was cobalt ferrite, silicon carbide, and barium titanate nanocomposites. Now, I'll be going into the following experimental techniques one by one. So let's look at the results of the first experimental technique, that is X-ray diffraction. Now on the screen is the X-ray spectra of our nanocomposites. I would like to highlight this. This is the 100% cobalt ferrite, and here we have introduced 10% barium titanate, 20% barium titanate, 30% barium titanate, and 40% barium titanate. Now the other two components were kept in equal percentage. For example, if here we are having 10% barium titanate, 40% silicon carbide, and 45% silicon carbide and 45% cobalt ferrite. And in the same manner, we have created this nanocomposite series. Now, in the spectra, we can see that for 100% cobalt ferrite, a peak broadening, a very prominent peak broadening was observed. Now, this is also an indication and proves the fact that the compound, the material that we have synthesized is in the nano range. However, this peak broadening was not so prominent in the composites. So this tells us about the relative particle size of the nanocomposites and the synthesized nano materials of cobalt ferrite. So we have done JCPDS matching with appropriate JCPDS files for cobalt ferrite, silicon carbide, and barium titanate here. And with the matching, we could conclude that the emerging 2 theta positions confirmed the presence of cobalt ferrite, silicon carbide, and barium titanate in the nanocomposites. We have already discussed that the broadening in the peaks was obtained for cobalt ferrite, which depicted the formation of nanoparticles. The broadening was not so prominent for the nanocomposites, which indicated the increase in relative size of the particles. So when we synthesized the nanocomposites, we figured that the size of the particles has increased. Now, this is the UV visible spectra. And on the screen, we have UV visible spectra in the range 200 nanometer to 500 nanometer. And by this measurement, we could find out that the absorption edges for the composites were found in the range 200 nanometer to 300 nanometer. And we could conclude that the absorption of the light is happening in the low ultraviolet region. So this was the first optical study that we performed. We are also trying to understand more about the UV visible spectra. The analysis is still under progress. This is the FTIR spectra of our nanocomposites. And we have tried to identify all the peaks, and the peak positions have been showcased in this table. And again, we could figure that for 100% CFO, the peak here, we can also look at the exact wave number here from the table. 338.65 peak tells us about the OH stretching vibrations interacting through H bonds. And this was observed, and we have also tried to take help of some research papers in order to validate whether the peak positions that we are getting are analogous to their data or not. And we found out that the peaks were very near to this range, 3338.65 per centimeter. And the absorption band was found at 1738.51 per centimeter. Now, the further analysis of this nanocomposite series is under progress. And now I'll jump to the dielectric measurements part. We have also performed this characterizations, dielectric characterizations, in order to understand what are the dielectric characteristics of our nanocomposite series. So on the screen, I'm presenting dielectric permittivity and dielectric loss of our nanocomposite series. Now we can see from the figure that for 100% cobalt ferrite, the dielectric permittivity was found to be 0.42. And for 10%, the highest permittivity obtained was 2.4. For 20%, it was 0.16. For 30%, it was 3.0. And for 40% BTO, it was 0.90. And the corresponding dielectric losses is also plotted in the right. Now, some uniform trend was not obtained, and what we could deduce from that is that In this nanocomposites, we have role of two composites playing here. So with the cobalt ferrite, we have barium titanate and silicon carbide. So here, when one part is playing a major role, the other part is inhibiting its role here. And the trend, as we are increasing the percentage, is reversing. So that was the idea we used, and we tried to understand why we are getting the data like that. So I would like to conclude my presentation here. We successfully synthesized CFO, cobalt ferrite, silicon carbide, barium titanate nanocomposites at varying weight percentage of barium titanate. The XRD spectra confirmed the formation of nanocomposites, and peak broadening assured the presence of nanomaterials. Optical studies were showcased here, and the dielectric permittivity and loss tangents were also successfully presented. Thank you so much. I'm done speaking.
Yeah, thank you, Rishiraj.
Yes.
You have done a very good presentation. Nice presentation it was.
Thank you so much. Thank you, sir.
So I have a couple of questions. I have a couple of doubts, not questions.
Yes, sir. Yes, sir, please.
So first was with the result of XRD.
Yes,
there was two questions I have. First
yes.
one, how can you ensure the formation of the composites from the result of XRD first? And the second was how the broadening happened when you make the nano composites.
So, sir, I would like to take the second question first. So, the broadening, when we are talking about the broadening part, there is lattice inclusion of lattice strains in our particular nanomaterials, and the inclusion of lattice strains, be it tensile or compressive tensile and longitudinal strains, and these strains are found to have a dominating role when we are talking about nanomaterials. So, and we have a supporting literature which states that these peak broadenings assure us the presence of nanomaterials. So, sir, I hope I was able to answer your question.
Okay.
And sir, the first question which you asked, nanocomposites, how I'm assuring that whether my nanocomposites series is made or not. So I have analyzed it thoroughly and tried to check my peak positions with individual JCPDS data of cobalt ferrite, silicon carbide, and barium titanate. And the respective peaks were identified for the individual components. That is how I'm saying that the nanocomposites are there. Inclusion of all the three elements is there in the nanocomposites.
Okay. That means you need more analysis, I think. You need a high resolution images, microscopy images.
Yes, sir. Yes, sir. We are looking forward
for assuring the formation of nanocomposites.
Sir, we are targeting FESEM because good resolution.
That's better. That's better.
Yes, sir. Yes, sir. Yes, sir. We are trying to do that.
Another one with the dielectric results.
Yes, sir. Yes.
So, what is the reason of possible changes like this with the formation of composites? I mean,
sir, like I mentioned in the presentation also, like the change is not uniform. But the possible reason what we figured could be here the number of compounds we are using is 3. It's not a binary composite, but it is a ternary nanocomposite. And such results have been achieved in other literature also, where ternary nanocomposites are found to give dominating roles by particular compounds sometimes and the other compounds at other times. So that was the possible explanation we could found for this type of irregularity in the data.
Okay.
Yes, sir.
Dielectric permittivity. Okay. Thank you.
Thank you, sir. Thank you so much. Sir, may I leave?
Yes, I hope all of you have finished. All the participants finished their presentation. So
Okay.
Pushpendra. Yeah,
Yes, sir, we are done with today's presentation.
yeah, okay.
Okay. So, sir, I would like to thank our session chair, and I would also like to thank all the participants for presenting their work. And I kindly request our session chair to please share the marks detail via email with me. And now I request our IT team to end the session. Thank you so much for joining, everyone.
Okay, right. Thank you.
Session. So today we have with us Mr. Dr. Josie Joseph, and let me introduce you in a brief. Dr. Josie Joseph is an assistant professor at Department of Physics in Neelambagiri College, Kerala. Dr. Joseph has joined this prestigious college in year of 2013 after serving as an assistant professor at NRI group of institutions at Bhopal. In 2013, he received his PhD studies of novel core cell hetero nanostructure employing magnetic and semiconducting materials. He received his master's degree in physics in 2006 and also received his MPhil degree in 2007 from Barkatullah University, Bhopal, India. Sir has completed and worked on various research projects and also worked on some sponsored project from UGC for 2 years. Some of his work include research on investigation of structural, morphological, compositional, and luminescence behavior of zinc oxide nanoparticles with and without hydrogen hydrate tetride. And as of now, sir has a total of more than 10 research paper in hand. And now I'll hand over to the sir so he can start with the further progress of the session. Sir, over to you.
Thank you. Audible? Is it audible?
Yes, sir, you are audible. We can start.
Okay. Thank you. Welcome to all to the International Conference on Advanced Materials in Innovative Technology. It is my great pleasure to be here as a part of this conference. I am also express my great gratitude to the conference team for inviting me. I am also express my sincere thanks to Dr. Deepshika. She was my PhD mate. As we know, we have 6 presentations right now. The presentation will continue for 10 minutes and 2 more minutes for the interaction. Hope all presentation will give more input to the audience. Once again, welcome to all young scientists in the area of material science. So we will start for the first presentation. Thank you.
Good afternoon, sir.
Good afternoon.
Screen is visible, sir.
Yes.
Sir, good afternoon, all of you. Thank you for giving me this opportunity. Myself, just 1 minute, sir. So, good afternoon, all of you. Thank you for giving me this opportunity. Myself, Ashok Kumar, and here I am representing our research paper titled Enhancement of Nonlinear Effects in Traveling Wave Tubes for Space Applications. Dr. Renu Sharma, Dr. Amitav Roy Chaudhary, and Dr. Nitika Chaudhary are my co-authors for this paper. The conventional vacuum tubes like triodes, tetrodes, and pentodes were used as single source for low output power at low microwave frequencies. But at present, the linear beam tubes, O-type tubes, are the most important microwave tubes. Traveling wave tubes are also O-type tubes. These are used for high frequency bandwidth, high gain, low noise, and low to moderate peak and average power. traveling wave tubes are basically two types, helix traveling wave tubes and second one is coupled cavity traveling wave tubes. In this paper, we discuss about KU band helix traveling wave tubes operating frequency 10.9 GHz to 11.7 GHz, modeling, simulation, analysis and outcome results. We start with the introduction of traveling wave tubes. Basically, traveling wave tubes are broadband microwave devices which are different to clystrons because these have no cavity resonators as clystrons, in which amplification process take place by interaction between electron beam and radio frequency field. Future communication systems basically requires multi-channel power amplifiers जिससे data packages can be processed with higher streaming rates and greater capacity, which requires data streams will be broadband, specifically modulated and low noise and produce greater output power. But solid state amplifiers are limited due to their overall frequency at both output powers and frequency bandwidth. All these limitations can be removed by using helix traveling wave tubes. Now we discuss about the constructions of a basic traveling wave tube. In the following diagram, we can see that a traveling wave tube which have helix slow structure has different components like electron gun with cathode, input RF signal, output RF signal, and helix as a slow wave structure and attenuator to focus the beam and collector to collect the electron beam. Electron gun from a cathode tube which focus the electron beam in the gap between anode plates to helix and that is collected by a collector. Basically the work of electron cathode tube is to produce electron and electron gun focuses these electrons. Magnetic field guides electron beam to focus without scattering and helix works as a slow wave structure. Applied RF field generates or produce an electric field at the center of helix. This resultant electric field travels with the velocity Vp, which is called axial phase velocity. The value of axial phase velocity can be given by the following formula: Vc in multiplication with pitch upon the circumference of helix. The circumference of helix is given by 2 pi r, where r is the. Now we discuss about the segment electrode arrangement in TWT. Now we will discuss about the operation of traveling wave tube. When anode plates at zero potential, axial electric field will be at node and the velocity of electron beam does not affected. But at the point which axial electric field at positive antinode, electron moves in the opposite direction, electron accelerated and try to catch the late electron that encounters the node of RF axial field. But at point which axial electric field at negative antinode, electron tries to overtake and electron receives modulated velocity and a second wave is induced in the helix and and the output becomes higher than input and amplification take place. These are the some applications of traveling wave tubes. Traveling wave tubes are used in microwave receivers and wideband communication links, coaxial cables, in communication satellites, in troposcatter links, and in high power pulse radar and ground-based radar. Now we discuss about the design of our traveling wave tube. basically 4 factors which we will consider during the designing of traveling wave tube and try to achieve them. High efficiency, high gain, medium to high power, and broad bandwidth. In this traveling wave tube, the main components of electron gun that we used is a Pyris type low prevalence electron gun with M type dispenser. Cathode operating temperature is almost 950 degrees Celsius and low heater power 3.5 watt is used. Due to this, the lifetime of traveling wave tube can be longer. Also, we use electrically isolated beam focusing electrode BFE. Other components are input RF couplers, which are SMA type coaxial couplers, and output RF couplers are TNC type with WR75 waveguide. Helix slow wave structure, integral pole piece IPP barrel assembly, samarium cobalt periodic permanent magnets, beam refocusing section BRS, multi-stage depressed collector MDC with the base plate and isotropic fin type radiator. These are the specification of these all components which are used. For designing and analysis, we use 3 software packages mainly. These are Sunray 1D, CST Microwave Studio, and HFSS. I try to describe all software packages in short. Sunray 1D is a simplified 1D large signal code which measures loss and circuit variation along the tube along with input and output coupler mismatch के कारण जो backward wave and reflections होते हैं उनका भी measurement कर सकता है. CST Microwave Studio fully featured सॉफ्टवेयर है इलेक्ट्रोमैग्नेटिक एनालिसिस के लिए और डिजाइनिंग करने के लिए ट्रेवलिंग वेव ट्यूब को हायर फ्रीक्वेंसी रेंज में. ये it is basically based on ACIS modeling kernel, and HFSS is a 3D full wave electromagnetic field solver for high frequency and high speed electronic component designs. It is based on 3D full wave finite element method FEM field solver. Now we discuss about the parameters which are used in the design of RF section or slow wave structure of helix. Operating frequency will be 10.9 to 11.7 gigahertz and bandwidth is 0.8 gigahertz. Power will be almost 140 watt. Beam voltage is used 5.8 kilowatt. Beam current will be 95 milliampere. Beam radius parameter 0.34 millimeter. Beam filling factor is 0.50. Tunnel radius is 1.124 millimeter. Barrel inner radius is 3.5 millimeter. Helix inner radius is 1.1 millimeter. Helix tap thickness is 0.15 millimeter. Helix tap width is 0.30 millimeter. Support rod type is T-shaped and pitch profile P0 equals to 0.54, P1 equals to 0.57 and P2 equals to 0.50. Previous value is 0.224 micrometer. Now we discuss about the pitch profile and loss profile for this Helix TWT. Helix pitch, 3 Helix pitch P0, P1, P2 are observed. P0 is 0.54 millimeter, which is due to growing wave section propagation constant, and P1, which is 0.57 millimeter, is corresponding to bunching section propagation constant, and P2 is 0.50 millimeter, which relates to power abstraction section propagation constant. The total circuit central loss is 60 decibel and the circuit loss is 2 decibel per inch. All these analysis work is done by the using Sunray 1D code. The results which we get from this traveling wave tube are as follow as iris gain is 0.0834, output power is almost 52 decibel, saturated gain is almost 25, and efficiency of traveling wave tube is almost 26%. Gain flatness is 0.8 decibel per gigahertz, and phase shift is 45 less than 45 degree. And AM and PM curve characteristic is less than 3 degree per decibel. Phase shift from saturation to 20 decibel is observed under 40 degrees. These are the references which are used in this research work. Thank you.
Thank you, Mr. Ashok. Now it's a time for the question. If anybody have any doubt or any clarification, this is the time for that. Okay, if nobody have any doubt, we can just close this presentation by saying thanks to Mr. Ashok. Anyway, little bit this presentation was good in related to the nonlinear. It was thought that this was related to nonlinear optics. Anyway, is any relation to this nonlinearity to any nonlinearity optics?
No, sir. This is basically traveling wave analysis, which is based on microwave. इलेक्ट्रॉनिक्स एंड कम्युनिकेशंस के अंदर सर माइक्रोवेव डिवाइसेस है, जैसे पहले कन्वेंशनल यूज होता था, अभी ट्रेवलिंग वेव ट्यूब्स यूज होता है, उसका पार्ट है सर। इसका ऑप्टिक्स से सर इसका ज्यादा कोई रिलेशन नहीं है, इसका सर इलेक्ट्रोमैग्नेटिक रेडिएशन इंटरेक्शन से रिलेशन रहेगा।
ओके, थैंक यू एंड ऑल द बेस्ट।
थैंक यू फॉर योर प्रीशियस टाइम। थैंक यू सर।
ओके, वी विल
कैन आई लीव सर?
हेलो,
हाँ, can I leave, sir?
Yes, sure. Okay,
thank you, sir.
We are moving for the next presentation, and the next presenter is, I think, Sambit Swing, or
yes, sir.
Who is going to present next? Sambit Swing?
Yes, sir.
Okay. Thank you. Welcome. Now over to Sambit Swing.
Sir, is it visible?
Yes.
Okay. So good afternoon, everyone. I am Sambit Swang, and I am giving a presentation on the effect of reinforcement type and composition on microstructure and mechanical properties of copper metal matrix based composite using powder metallurgy route. Now, composite is the combination of two or more different metals which are physically distinct by certain boundaries. And the main objective of composite is to achieve the properties of both matrix as well as reinforcement. So in the metal matrix, composites are used because they have higher temperature capability and higher strength to weight ratio, including wear resistance. The copper metal matrix composite is the most promising material for many engineering applications due to its good microstructural stability at high temperature and also thermal and electrical conductivity. So the preference of the reinforcements includes ceramic particles, which are determined by their microstructure, mechanical and typological properties. The powder metallurgy route, it is a process of forming precise metal products from the metal powders. And here the metal powders are mechanically milled and then pressed into a desired shape. Then it is followed by a heating process called sintering, and extra secondary operations can be operated to relieve some stresses. Now, so first is the ZrO2 reinforcements. When we add zirconium dioxide in the copper
matrix. So nearly spherical zirconium particles are homogeneously distributed in the copper matrix. Here the specific electrical resistivity and hardness of the copper zirconium dioxide nanocomposites increases with increasing oxide particle content. The dispersion of ZrO2 nanoparticles yielded good wear and wear resistance for the surface composites when compared with soft copper matrix. Also, the coefficient of friction indicates small degradation with the dispersion of ZrO2 in the copper matrix. Accordingly, the Won surface analysis shows that when only copper was used, there is ploughing of materials as delaminations and there are grooves are present. But when ZrO2 is added, there is it as ZrO2 offers lubricating effect, so there is a smooth surface finish. Next is MOS2 reinforcement. When these molybdenum disulfide are added, so in this microstructure we can see that the continuous matrix phase present in these two images is changing from continuous matrix phase from copper to MOS2. Means when MOS2 percentage is increased, MOS2 becomes the reinforced becomes the matrix and copper becomes the reinforcement. As MOS2 is a softer phase, so in these phases the hardness is less. Now both the coefficient of friction and wear loss is decreased by all the applied normal loads. And the high content of MOS2, however, contribute to the reduction of wear resistance due to reduced hardness of the material. Now in the wear mechanism, when MOS2 is present in 2%, we can see that the lubricating film is present and there is shallow abrasive marks. But at more percent of MOS2, delamination occurs because here the soft particles of MOS2 are present more. Now, titanium carbide plus graphite reinforcements. Here we see that there is uniform distribution and absence of cracks, and there are strongly interfacial contact between the matrix plus reinforcements. These graphite flakes are present along with titanium tube structures. Here also the increase in hardness of this is dependent on the titanium carbide particles and its uniform distribution, because graphite is a softer particle and it actually decreases the hardness value. The wear rate means there is an increase in wear rate with increase in load. The wear resistance increases along with the hardness, but if graphite percentage is more, the wear resistance decreases. And where the graphite present also provides good lubricating effect. So after the wear function, there is a smooth surface finish in the wear mechanism. Silicon carbide reinforcement. Silicon carbide is usually used when we need grain growth, and because it improves the thermal stability of the nanocomposite. The grain size decreases, so it increases the hardness. Now the addition of up to 2% SiC nanoparticles results in increasing in hardness value, because higher SiC will agglomerate and they form clusters, which decreases the hardness value. Here the major wear mechanisms are considered to be flake formation and abrasion. With increasing silicon carbide volume percent, the flake percent would diminish, and also with the decreasing load and increasing the SiC volume, the coefficient of friction in the copper nanocomposite increases. TiB2 reinforcement. TiB2 is usually used along with a copper tungsten alloy matrix, because TiB2 provides a thermodynamic stability, and there is a homogeneous dispersion of tungsten carbide. But when TiB2 is added, it reduces the mobility of the grain boundary energy and it obstructs the dislocation motion, thereby for cluster formation is decreases in the microstructure. The inclusion of TiB2 in the copper matrix reduce the wear rate of composite samples. The increase in wear resistance for the composite samples was attributed due to the presence of hard nature of TiB2 particles. In the wear mechanism, because there is a presence of reinforcements which get ejected from soft matrix, they form mixed layer. In these cases, the wear resistance increases. copper nanotubes. Addition of copper nanotubes to copper refine the grain size, and when copper nanotube percentage increases, they form clusters, and these agglomerates number increases. As the CNT has a very high van der Waals force, so they have a strong tendency to cluster and agglomerate. Hardness of the nanocomposite increases just up to a certain point. Also, the electrical conductivity of the nanocomposite decreases because due to agglomeration, blocking of particles in the united matrix occurs. The tribological property is good here, as the strengthening effect of CNT through load transfer mechanism is occurring, and CNT also act as a solid lubricant. So the wear rate and coefficient of friction decreases. And these the wear mechanism here shows that without the addition of CNT, the groups, these are the groups present, but after CNT addition, it forms a lubricating layer. But increasing in the CNT also increases the agglomeration, and it can cause delamination wear and formation of cracks. So as CNT volume increases, it causes delamination and agglomeration. So to minimize it, silicon carbide particles are used, because the almost spherical sized silicon carbide particles break up the agglomeration of the carbon nanotube clusters, and they create local shear stress and uniform distribution of matrix. These images show the pore-free structures, and as they have strong interface contact was established. As silicon carbide is one of the hardest ceramic particles, so the nanocomposite hardness also increases. The wear and friction coefficient also shows that reinforcing phase act as load bearing elements, so they reduce the contact area with the sample surface, and the wear resistance is reduced. But and also in the wear mechanism, when only small amount, when no silicon carbide was embedded in this, it shows a constant and uniform surface on the lubricant layer, and the debris is also small in size. But as we increase the copper nanotube, there is agglomeration formation and delamination occurs, and it may act as stress concentration sites, and formation of crack can start. So conclusion, here means the powder metallurgy route is one of the easiest synthesis route for metal matrix composite, because here we don't need to melt the materials, and the proper bonding between the matrix and reinforcement of the particles is established, so we can get a homogeneous and uniformly distributed matrix and reinforcement phase in the microstructure. The choice of reinforcement material is highly influenced by their mechanical properties, and also in case of hybrid reinforcement, where we use two reinforcement in a single matrix, it can also increase electrical and thermal properties of the material as compared to its base material. So yeah, these are the references. Thank you.
Okay, thank you, Mr. Swain. This is the time for any clarification or questions from the dais. If nobody is going to ask any question, let's have one clarification. Mr. Swain, is the whole work which has been described is done by you, or it is something literature review?
Yes, sir.
Is it a literature review?
Yes.
Okay, because most of the figures don't have any reference. That's why I was little bit confused with is it your work or okay. Anyway, it's your, maybe you are starting of your, what is your stage in research?
Yes,
is it?
sir.
It is a start. It is a starting.
Yes, sir.
Okay, and what is the preparation method for all the material used here? For is it just this is a mixing with
This is a powder metallurgy. Yeah.
This just a mixing.
Yeah, mixing in a mechanical milling machine.
Okay, okay. What is the criteria for this mixing? How much time will, and what is the different conditions?
that depends, means the speed of rotating the milling machine and also how much time to rotate. Mean it will decide the grain size.
Okay, okay. And how you will find out the grain size?
Particle size analysis can be done.
By which method?
Particle size analysis, or we can also take means SEM images of the powder sample before milling and after milling to find out the grain size. Is it decreasing or not?
And we are not going to XRD or any TEM.
Yeah, we can do XRD to find out that if any means other than these elements or any oxides or anything is forming.
Okay. Okay, Mr. Swain, it was a nice time with you. Thank you very much. And we will go for the next presentation. Thank you. Okay, and who will be the next? Hello, is it Arvind Dhruve or someone else?
Yes, sir, it's Arvind Dhruve.
Okay, okay.
Hello. Sir, I am
Hello.
audible?
Yes, yes. Okay.
Okay. Thank you. Sir. Thank you. Sir, my screen is visible?
Yes, yes. Okay, let's start.
Okay. Okay. Thank you, sir. Thank you so much. Myself, Arvind Dhruve. I am a research scholar from Department of Physics, APS University, Diva. My presentation topic is long-term changes in solar wind plasma parameters with cosmic rays and solar cycle 24. My outline, my topics presentations outline is introduction, cosmic rays and its variation, solar activity cycle 24, and solar wind parameters, data selection and methodology, result and conclusion. Firstly, in introduction, cosmic rays are a high energy particle which are falling on the Earth's surface all the times and everywhere. Cosmic rays discovered in 1912 by Victor Hess, who in 1936 was awarded the Nobel Prize in Physics for his discovery. Cosmic rays energy range is 10⁻⁷ to 10⁻20 electron volt. Origin, cosmic rays is a still unsolved problem, and cosmic ray composition is 92% proton and alpha particle 6% and heavy nuclei 1%. This is composition of cosmic rays, and its classification 2 types: primary cosmic rays, secondary cosmic rays, 3 types, sorry, and solar cosmic rays. Cosmic rays intensity is variation, basically 2 types: periodic and sporadic variation. Periodic variation 11 and 22-year variation, and 27 days variation and daily variation. Sporadic variation, Forwood decrease, ground level enhancement, and transition variation. In this study, we used 11-year variation. Solar. Firstly, we explain what is a solar activity cycle 24. Solar activity is a sum of phenomena driven by the sun's magnetic field. The magnetic field which goes through a cycle called the solar cycle, and every 11 years or so, the sun's magnetic field completely flips. That is, the sun's north and south poles switch places. Then it's take out another 11 years for the sun's north and south poles to flip back again. According to this diagram, solar activity is measured by the number of sunspot. Sunspot, this is the spot, number of spots which find in the surface of the sun follows and sunspot. So in the sunspot, number of sunspot rise and falls, rise again in the about 11 years. This is due to the variability of the solar magnetic field. And solar flares, coronal mass ejection, high solar wind, and solar energetic particle are the form of the solar activity. All solar activity is driven by the solar activity magnetic field. Solar wind plasma parameter basically is a stream of charged particle ignited from extremely hot corona in the sun. Actually, corona is the outermost surface of the sun. The solar wind consists of charged particle, primary electrons and protons following outward from the sun. It contains a large amount of kinetic energy and electrical energy. The main indices used to measure variations in the Earth magnetic field strength are TST index and AI index. Disturbance says in solar wind plasma speed, density, temperature, pressure, and interplanetary magnetic field and geomagnetic storms are associated with disturbances in solar wind plasma parameter. Basically, cosmic rays when entering heliosphere are modulated by interplanetary magnetic field, which is carried out away from the sun by the solar wind, and coronal mass ejection are the drastic solar events in which amount of solar plasma material are ejected into the heliosphere from the sun and are mainly responsible to the generate large disturbances in solar wind plasma parameters and geomagnetic storm in the geomagnetic field. CME, coronal mass ejection from the sun, drive solar wind disturbance in terms of the magnetic field, speed, density, temperature, and pressure, which in turn causes a geomagnetic disturbance in Earth. Solar wind parameters play a crucial role in generating geomagnetic storm, and W. Gonjat reported that there is a strong relation with interplanetary magnetic field. Therefore, in this paper, we are a study, correlative study has been performed to get variation of cosmic ray intensity along with the solar wind plasma disturbance with geomagnetic parameters. So the aim of the proposed work is to analyze the solar wind parameter correlation between variation of cosmic ray intensity during solar cycle 24. We are use data selection methodology here. We have taken cosmic ray data from Aulu neutron monitor, which has cutoff rigidity 0.81 gigavolt. This is the website. And OmniWave data in this study, sunspot number, solar wind plasma perimeter data have been taken from the database website OmniWave in the basis of annual average basis. Data analysis is done by using the statistical techniques to correlate and analyze them, the cross correlation method and scattering regression method. In this study, mainly focus on the relation to solar wind plasma parameter. These graph shows the cosmic ray intensity variation during solar cycle 24. Resolution with 1 year. In this, hello, sir, I'm audible. Hello.
Yes, continue.
Okay, thank you, sir. This graph shows cosmic ray intensity variation during solar cycle 24 with resolution 1 year. In this graph, variation from 2008 to during solar cycle 24 shows we have correlated cosmic ray intensity and sunspot number during solar cycle 24 and cross plot and correlation between both CRI and SSN and find correlation coefficient between cosmic ray intensity and sunspot number minus 0.937. Very strong negative correlation obtained from CRI and sunspot number. Secondly, variation of cosmic ray intensity and interplanetary magnetic field magnitude during solar cycle 24. We have get correlation and cross plot here plot, and we find correlation coefficient between cosmic ray intensity variation and interplanetary magnetic field minus 0.849, strong negative correlation. Then correlation between cosmic ray intensity and solar wind speed during solar cycle 24 and plot cross plot between both cosmic ray intensity, solar wind speed. We find here cosmic ray intensity and solar wind speed के बीच में जो correlation हमें प्राप्त हुआ है, so very big negative correlation. Then we have used data parameters solar wind temperature and cosmic ray intensity and get correlation between both cosmic ray and temperature minus 0.373 is very big negative correlation. Then fifth parameter we use solar wind pressure and plot graph between cosmic ray intensity and solar wind pressure and found correlation between both big negative minus 3.389 and last next cosmic ray intensity and distortion storm of time. We get a strong correlation between both 0.887. Then last auroral ejection and cosmic ray intensity variation, we found correlation weak positive relation 0.311, and these are the parameters we determined cosmic ray intensity and sunspot, cosmic ray and interplanetary magnetic field. We found here strong negative, and last cosmic ray and DST we found a strong positive correlation. Conclusion: on the base of on the various static and linear regression method, we found that cosmic ray intensity and sunspot number RZ are inversely correlated, and correlation coefficient is found R is equal to minus 0.937 found between cosmic ray and intensity and sunspot number. The correlation between IMF and cosmic ray intensity are strongly anti-correlated, and also the coefficient of correlation is high, minus 0.849 during the solar cycle 24, and disturbance storm time shows a strong positive correlation are 0.887 with cosmic ray intensity for the period 2008 to 2019, which called solar cycle 24. Here very good correlation was obtained, the correlation between solar wind speed and cosmic intensity are weak, negatively correlated, and also the coefficient of correlation are minus 0.112 during the solar cycle 24, and a weak correlation we found are minus 3.373 found between cosmic ray and solar wind temperature during the solar cycle 24. And from the analysis, weak positive correlation have been found between cosmic ray and auroral ejection, which are associated with the cosmic ray, solar wind with correlation coefficient R 0.311, and a weak negative correlation with a correlation coefficient of minus 0.389 has also been found between pressure of solar wind and cosmic ray intensity. Thus, we can say that the study of the long-term changes in solar wind plasma and CRI, cosmic ray intensity, help us to better understand the significant new insight on how different solar wind parameters affect the heliosphere. And heliosphere is a region surrounding the sun and the solar system that is filled with solar magnetic field and the protons and electrons of the solar wind. So as well as solar and geomagnetic activity, solar cycle 24 has initially displayed much less activity. Then, thank you.
Thank you, Mr. Aravind. Now it's the time for any questions.
Hello.
Hello, yes.
Yes, sir.
Okay, if anybody have any clarification doubts, may please ask. We have one question is why the data is only for 2019?
No, sir. We have take yearly data, yearly annual average data from 2008 to 2019 during solar cycle 24. Currently ongoing solar cycle 25.
Okay, we are restricted our data only for that type.
No, sir. Actually, my research on only solar cycle 24. So we have taken data solar wind plasma and solar activity and cosmic ray data during this period.
And one correlation function is in the graph is in between temperature and pressure is also where the temperature and the pressure is for which region?
Sir, temperature and pressure are the solar wind plasma.
Solar wind plasma.
Yes.
Okay. And the correlation is we have two types of one is positive and one is negative.
Yes, sir.
On what basis maybe the positive and the negative correlations are coming? Is it any reason or is it for any conclusion? It's maybe like due to this parameter. Sometimes it's positive.
Actually, sir, positive and negative. If we get a positive correlation between both the cosmic ray and second solar wind parameter, so we have we can say that solar wind affected the cosmic rays.
Okay. Okay, Mr. Aravind. Anyway, I have done my PhD in Bhopal. I have a close with some friends in Riva. Thank you very much, Mr. Aravind.
Okay. Thank you, sir. Thank you so much. Starting है sir मेरा अभी.
Sure, all the best. And
thank you, sir.
Do you have any relation or any connection in BU Varkatala University? I think there is a atmospheric research area. It was in plasma research area maybe.
सर अभी तो नहीं है सर, बट मैं कोशिश करूंगा. अभी स्टार्ट किया है सर, वहाँ पर होता है स्पेस फिजिक्स में, वहाँ भी काम होता है. तो मैं जरूर कांटेक्ट करूंगा सर.
Okay. Thank you, Mr. Arvind. Thank you very much.
Okay, thank you sir, thank you so much. Can I leave sir meeting?
Sure.
Okay, thank you sir, thank you so much.
I think our next presentation maybe by Mr. A. Nilufar, is it?
Sir, actually, he's not present right now. We can skip his name and
Okay.
continue.
Okay. And I have only one last participant, that is Pradeep Tanwar, since I have the fifth one is blank.
Sir, in the blank one, it is Mr. Hariom Pamar.
Hello.
Okay. We can have Mr. Hariom's presentation. Hariom.
Very good evening, sir.
Okay, good evening.
Nice to see you again, sir, after the Kannur conference. So I'm here to let me share my screen. Sir, is it visible?
No. Yes. Now it's
Yeah. I'm here to present my research work in the international conference. And my title is The Effect of Temperature on Optical Energy Bandgap of Barium Titanate Nanoparticles. These are the outlines over which I will discuss my research. So first of all, the introduction. The barium titanate is very fundamental ferroelectric material because it has the property that it contains the dipole at even the room temperature without any presence of any external electric or magnetic field. Due to that, the barium titanate in nanoscale reveals many novel physicochemical properties such as the electrical properties, magnetic properties, dielectric properties, and electrical properties, which are very difficult to obtain from their bulk forms. So in nanoscale, the synthesis of barium titanate is very useful, and rather than here, if we see the application part of the barium titanate, so this time this barium titanate nanoparticle can be very useful for the fabrication of capacitors, transducers, sensors and actuators, and etc. So over which I just started to search something. So these are some objectives. First objective is to synthesize barium titanate nanoparticles using soul gel techniques with varying the temperature. And then after properly synthesizing samples, I have investigated the effect of temperature on its optical energy bandgap. This slide contains the methodology of formation of barium titanate nanoparticle by the soul gel route, and the whole process was contained in 3 steps. Firstly, in the first step, we have taken the precursor and barium acetate and heated at 65 degrees centigrade with stirring, and then just cooling it at the room temperature. And then we have added the another precursor is the propanol and TTIP, and they just cool down the temperature at the low temperature. And then we got the optimum sol. For after that, just keeping it, we are getting the gel, and after drying and calcination, we are getting the barium titanate. So after getting the barium titanate in the form of powder, we need to characterize its physicochemical properties. So these are some results and discussions. The first one is the structural property that has been found with the help of XRD characterization. So if we see here that this A is a barium titanate synthesized with the help of soul gel method, which is dried at 100 degrees centigrade, and the peaks recognized as the formation of barium titanate is improper, and that is what the amorphous nature is showing here. But as the calcination temperature rising, So we are obtaining nanoparticle with the purity, and that temperature difference was from 600 degrees centigrade, even though time was also varied from 2 hours to 5 hours. And as the temperature increases from 600 to 800 degrees centigrade, we have found that the impurity was totally neglected, and the pure barium titanate nanoparticle has been synthesized, and that can be compared with the standard barium titanate, and we have got the matched. After all, we have calculated the particle size also, and that was observable that as the calcination temperature increases, the particle size also increases. Now, the next slide, which is represents the optical property. So here, this figure represents the absorbance spectra of barium titanate nanoparticle. And here, the first one is representing that this A1 is a barium titanate nanoparticle, barium titanate, which is commercially available. And we have obtained the absorbance space at 317 nanometer. And this is representing the amorphous form of the barium titanate. But if we see the second one, where the calcination temperature has been capped at 600 degrees centigrade, and the time was varied from 2 hours to 5 hours. So as the time was varied, we found that the absorbance is going to shift towards the lower wavelength. And rather, next we have changed the temperature at 800 degrees centigrade, but with the similarities were the time, and we have obtained that as a sample which was calcinated at 600 degrees centigrade, giving the absorbance age at 383 nanometer, but at 800 degrees centigrade for 2 hours, giving the absorbance age at 325 nanometers. And with the help of that, we have taken the extrapolation, and we found the band gap of the synthesized barium titanate nanoparticles. So that R seems that as the calcination temperature increases, the band gap are going to increase, and barium titanate nanoparticles synthesized at 800 degrees centigrade for 2 hours, having a nearly approximate band gap, which is of the standard one, that is a 3.9 electron volt. Second thing, we have correlated this optical band gap with the theoretical simulation process, which is the DFT. So here also this figure represents that. Yeah. So this figures also represents the correlation for the band gap, and that is what the graph between the energy versus the Brillouin zone. And here we have took the LUMO levels, that is the lowest unoccupied molecular orbital, and the HOMO levels, and we have obtained the difference between these, and we found the band gap of the prepared barium titanate nanoparticle based on their data. So we found the similarity of the band gap as we have calculated from the UV visible spectroscopy. Similarly, if we see the next diagram, that is yes, this density of state versus the energy. So here also we are getting two bands, which are the valence band and conduction band. The first conduction band is from the 0.1 electron, 0.5 electron volt to 17 electron volt in at this region, and the valence band is from minus 37 electron volt to minus 1.5 electron volt. And we have also found that in between this conduction and valence band there is no lines of intermediate. That means that indicates that is a Fermi gap, and this is what the band gap actually. Now, on the basis of this, we have moved further for the dielectric properties, and the dielectric property has been investigated with varying temperature. So here we found that the four material, basically which one is a commercially available, and the temperature treated barium titanate nanoparticles at 600 degrees centigrade for 2 hours and 5 hours, and 800 degrees centigrade for 2 hours. So what are the basic features we are obtaining from here? That as the temperature increases from 30 degrees centigrade to 170 degrees centigrade, the dielectric constant is prominently decreasing. And the same patterns we are observing in the synthesized nanoparticles, But what is the specific thing is that the nanoparticles which are synthesized at 800 calcinated at 800 degrees centigrade for 2 hours, giving a low dielectric constant, and which is very good, and even at the low frequency. And as we move further, the frequency increases. So we obtain that the dielectric constant is almost constant just because of the interspatial polarization stopped here. And if we see the dissipation factor also, so same the property which we have obtained here, that the dissipation for the material which is calcinated at 800 degrees centigrade for 2 hours is very minimum, rather than the temperature which is lower than the 800 degrees centigrade, we found the more dissipations. So over which, if we compare the dielectric study at a specific frequency range, so we observe here we have taken 3 specific frequency, that is one is a 100 hertz, second is a 1 kilohertz, and other one is a 10 kilohertz. And what we observe here, that as the dielectric constant decreases with increasing the frequency initially, and then becomes almost constant. This is maybe due to the calcination effect of the given to the barium titanate, and this is what the findings, that at 800 degrees centigrade for 2 hours, which is giving a optimum value of dielectric constant. On the basis of this optical and dielectric property, we can found that what are the conclusions. So that conclusion is barium titanate nanoparticle has been properly synthesized with the help of Sol-Gel technique, and we found that the sample calcinated at 800 degrees centigrade for 2 hours is ultra pure. Now, on the basis of band structure, we observe theoretically as well as the experimentally that the band gap, calculated band gap is nearly same, which is obtained from the theoretical simulation from DFT also, and that is what the sample which is calcinated at 800 degrees centigrade for 2 hours is giving the band gap almost nearly equal to 3.67 electron volt, and that is what we achieved with the help of calcination temperature effect. And the major important conclusions drawn from the dielectric study, we observe that the dielectric constant decreases and energy band gap increases as the particle size increases in the all synthesized barium titanate nanoparticles at the frequency as well as in the temperature. And the second thing is the barium titanate nanoparticle, which is calcinated at 800 degrees centigrade for 2 hours. It's very pure and having a optimum value of dielectric loss than the others. So on the basis of this conclusion, what could be the future work is that this nanoparticle, which is calcinated at 800 degrees centigrade, can be utilized as the sensing material for the detection of some gases at the room temperature. That will be done in the future. This is the acknowledgement. I would like to acknowledge SCRB for the funding and DAE CSR for providing the characterization facilities. These are some references. Thank you.
Thank you. If anybody have any questions, it is the time for. I have one doubt. Since it is generally acceptable that if the nanoparticle is under temperature calcination, the size of the particle size is generally increased.
Yes, sir. In my case also, the particle size is increasing.
Sorry, I am not getting.
Sir, am I audible to you?
Yes, now it is.
Yeah, sir, actually, in my case also, as I am increasing the temperature as a calcination temperature, and I am observing that the particle size is increasing.
Yes.
Yeah.
Okay. And if the particle size generally increase, the band gap will also decrease.
Band gap decreases.
Particles, the generally the relation is the particle size and the band gap is inversely proportional. Is mainly in quantum dot. The particle size is inversely proportional to the band gap.
Yes, but in quantum dot, that the size dimension is very less. But while I'm just calculated that particle size with the help of XRD data and we have with the help of Sealer method. But since when I go for the TEM analysis, then I observe that this particle size varies actually. So that particle size calculation with the XRD data is exactly not the authentic data. For that, I have to move for TEM analysis also.
What the time is pending?
Yes, sir, it is pending.
Is pending.
Yes, sir. TAM analysis, on the basis of TAM analysis only I will decide that whether I have to move for the gas sensing application or not. Yes.
Generally, it is shown that we can make different colors with the same nanomaterial with the different particle size.
Yes, sir.
We'll get violet, indigo, blue, green, yellow, orange. For example, using ZNS, using cadmium sulfide, we can make a different colors of the material with the same material. The only difference is the particle size. While we changing the particle size,
yes,
we
sir.
can tune the band gap.
Okay. Sir.
Okay.
Fine. Sure.
Okay. Thank you. Thank you, Mr. Hari.
Thank you.
Now we will move forward for the next presentation, and the next presentation will do by Mr. Pradeep Tanwar. Welcome, Mr. Pradeep Tanwar.
Hello.
Yes. Shall we start?
Yes, sir. Hello, everyone. My name is Pradeep Tanwar, and I am research scholar in J. Nayan Vyas University, Jodhpur. My subject of interest is transist metal ditriclosenide, in which today I will represent a small work on first principle study of structural and electronic property of TiSe2. First, we introduced transist metal dicyclosenide. In last few decades, 2D layer material graphene has raised extensively interest for promising application in energy storage and supercapacitive electronic device. Discovery of graphene make interest of researcher in new family of 2D nanomaterial. Graphene is a allotrope of carbon in which carbon atoms are arranged in two-dimensional honeycomb structure. But the main problem with graphene is it does not have a band gap. So researcher discovered some other layered material. My topic of interest is transitional metal dicyclosenide, in which I study Ti family. TMD is MXX2 type compound. That means it has a sandwich structure in which metal atom is present in between two chalconized atoms. This representation shows a simple primitive cell of TiSe2.
Mr. Pradeep, sorry to interrupt, but your slides are not moving forward. You are still on your first slide.
Okay, sir. Wait a minute, sir. Sir, now?
No, still on first slide.
I think, Mr. Pradeep, you have to click on the enable editing so that maybe the problem will be solved.
Okay, sir. Okay, sir. Wait a minute. So now it is okay.
It's okay. Okay, thank you.
Okay, sir. Here's some computational detail. We use quantum espresso for analyze TeSe2. TeSe2 has the P3ml space group. First, we converts the kinetic energy for TeSe2. E cutoff is determines the number of plane wave required to explain the wave function, because in quantum espresso I use plane wave method, in which we consider a plane wave and find the minimum ground state energy for material. For my case, I have 16 Rydberg for TeSe2. After conversion of kinetic energy cutoff, we move to conversion of K points. K points are hardly symmetric points in Brownian zones. And for TeSe2, we have 12, 12, 12, and 0, 0, 0 K points. In first three K point represent the folding factors, and last three represent the shifting factors. After K points, we calculate minimum value of lattice parameter on a different volume. We consider C by A. C by A is a lattice parameters in different axes. We consider C by A from 1.5 to 2 and find minimum volume and minimum energy for TiSe2. We get minimum value 454 mu cube and lattice parameter is 351 nanometer. After finding the minimum value of lattice parameter, we move to find optimum value of atomic position in unit cell for Ti and Se2 atom. By quantum espresso, we get 0.25. Here 0.25 represent the position of Se atom in Z axis in Cartesian coordinate system. This is band structure diagram for TeSe2. If we show this band structure diagram, we note that TiSe2 valence band and conduction band, both bands are just touched together. So we can say that TiSe2 is a semi-metallic material. So for conclusion, we get E cutoff is 16 Rydberg, K point is 12, 12, 12, and 0, 0 respectively. The optimum value for lattice parameter is 0.351 nanometer, and TiSe2 has semi-metallic properties. This is all from my side. Thank you, sir.
Thank you, Mr. Pradeep. If any have any clarification, otherwise, for the sake of interest, Mr. Pradeep, what is the meaning of minimum value of lattice parameter? What does it means?
Sir, my study is confined on theoretical aspect. We are just calculate the theoretical approach for material, because those materials cannot fabricate easily. So we calculate the minimum volume, because at the minimum volume we have minimum energy and we can easily fabricate those materials.
What is okay? That's okay, nice. But what is the meaning of minimum value of lattice parameter? What does it means? If we have a minimum lattice parameter, what is our advantages?
This shows that at this lattice parameter, material is more stable.
Okay, by that we can end our this section. I think I think Mr. Pushpendra, is it there?
Yes, sir.
Okay. By that, I think all of the participants has completed their presentation. Is it?
Yes, sir. Everyone has gone through.
Okay. Anyway, it is my great pleasure to be here.
Okay, sir. So, sir, I also thank you for giving us your precious time, and I would also like to thank all of the participants for presenting their work. And I request you, our session chair, Mr. Dr. Joseph. Sir, kindly share marking details with me. I have shared you updated the list of participants on your mail, and I also request our IT team to kindly end this session. Thank you, everyone. Thank you.
Thank you.